Welcome. My name is Katharina P. from Ilmenau, Germany, and I would like to present our latest investigations of the LED defect in indium-doped silicon. We use an excitonic photoluminescence line, P-line, that changes its intensity through elimination and annealing steps to determine an initial energy barrier of the defect using low-temperature photoluminescence. I want to give you a short introduction in our studies. There is a defect in silicon that reduces the absolute intensity, for example in photovoltaic tools, up to 2%. This reduced efficiency is called light-induced degradation. It is, for example, visible in the graph. Here the charge carrier lifetime is reduced during the elimination of boron and indium-doped silicon. And in the inset you can see that the charge carrier lifetime regains its initial value by an annealing step. This carrier lifetime degradation can be detected in both indium-doped float-zone and Strochalski samples, and could be perhaps the eye defect. Photoluminescence is a very sensitive tool to study impurities and defects in semiconductors, because the extrinsic or bound excitones have high recombination efficiency, so we use photoluminescence to study this defect. Briefly, I summarize the first results on indium-doped silicon. Light-induced degradation, LID, is also detectable in indium-doped silicon. The charge carrier lifetime is reversible by an annealing step. Both indium-doped Strochalski and float-zone silicon show lifetime degradation, and another result is that interstitial silicon is probably part of the defect. That we see in simulated concentration profiles of indium and recoiled silicon atoms. This observation we later use for our defect model. The next step was to investigate the photoluminescence line called P-line with low temperature photoluminescence. These three key properties describe the P-line. As you can see in the diagram, the P-line is only detectable in low-temperature photoluminescence spectra of indium-doped silicon. If the silicon wafers is doped with boron and gallium, or perhaps undoped, the P-line is not detectable. But notice, thallium also has a similar line. but won't show a electron hole liquid in this area. The second property or observation is that the p-line intensity changes during illumination and annealing steps. We called that LED cycle. And this intensity changes remind us of the charge carrier lifetime change. So we started studying this behavior during sample treatments, like in the lifetime studies. For example, with a short and long illumination steps and annealing treatments. At 200 degrees Celsius for 10 minutes, like in the studies by Sauer et al. The next behavior of the p-line we need for our studies is that quenching leads to an enormous increase in the p-line intensity. Because the p-line intensity in untreated samples is too small for calculating the intensity changes. But notice, the quenching only increases the p-line intensity, but is not its origin. Now, the question is, does the p-line show a LED defect configuration? We aim to answer this question by examining the change in p-line intensity during LED cycle treatments. The first observation we made during the illumination treatments. Here, the p-line intensity increases with short illumination and decreases with long illumination steps. The next observation we are able to make after the annealing processes. If you look at the diagram, you can see the normalized p-line intensity independent of the treatments. Here B stands for illumination and T for annealing steps. The p-line increases reproducible after short illumination steps. Followed by successive decrease of the p-line intensity at further annealing steps. This decrease of the p-line intensity we are able to measure in small steps. Therefore, we decide to focus first on the calculation of this energy barrier. To understand what the E52 energy barrier is, we need to take a quick look at the ICMSN defect model. Look at the diagram to understand the ICMSN defect. Here, AZ stands for the substitution acceptor at the lattice position of a silicon atom. in our case indium. The defect partner silicon is on an interstitial position SEI. The LED phenomena include the assumption that illumination activates somehow the defect in p-doped silicon, and annealing at moderate temperature leads to a deactivation of the defect. Following the ICMSN defect, the treatments allow the defect to change not only the charge but also its configuration. This configuration and charge change are reversible within LED cycle treatments. In the diagram, you can see 7 different charge states. The charge states can be reached after illumination or annealing treatments, are shown in blue for the positive, in black for the neutral, and in red for the negative charge state of the ICMSN defect. The neutral and negative charge state include 3 configurations. Okay. S1, 2, 3. The configuration changes can be achieved during illumination and annealing treatments. Energy barriers or activation energies must be overcome in this process. We identify the P-line as a neutral in the ICMSN defect in configuration S2, which binds the excitone. The intermediate state can be reached, for example, if the defect is in the ground state, after short illumination, or if the defect is in state 7, after short annealing. In the dark. Here, the density of the defect in this configuration can be estimated with the help of the P-line intensity. So, for understanding other configurations can also be present at the same time. The next, we quenched indium-doped float zone and Strochalski silicon samples, illuminated them for at least 2 days at 40 degrees Celsius, and then annealed them stepwise at different temperatures. Subsequently, we measured the measured data were fitted from the point at which the curve decreased using an exponential function. The determined rates were then plotted in the Arrhenius plot to determine the energy barrier. Now, these are our calculated results. The energy barrier calculated after fitting the measurement data is 1.07 for our Strochalski samples, 0.32 for our float-zone samples, and when we fitted them together, we get 0.78 electron volts. So the next question is, are there any difference between the samples that need to be taken into account? For example, the hole density. Hopefully, we can discuss this later. In summary, we could say that the P-line shows one LED defect configuration, and this LED defect configuration can be changed by LED treatments through elimination and tempering steps. We determined the energy barrier E52 between 0.32 to 1.07 electron volts. I would like to thank you for your interest in our study. If you would like to learn more about our defect study, please contact me.